Okay. Everybody in the back can hear me? Is it clear? All right. So before starting the presentation, let's, like yesterday, go back to the Google Drive, download the model. It takes like 1 minute, I think, so we can save time. If you go to OMT ETN 2017, in the software COMSOL, I put 1D photonic crystal. Don't mix them up. There is just one letter difference. Here I have put 3 files for you: parameters, band diagram, and the MATLAB code. You probably need band diagram, MATLAB, and the COMSOL model. And while it's downloading, let's start. Let me see if it works. Yeah. So you can see my first slide is very similar to what it was yesterday, only 1 letter difference. Yesterday was phononic, today is photonic. So I will be talking about periodic structures. Since yesterday I got some comments and some confusions about the origin of the band diagram, I want to give you a physical explanation of how, or maybe a more mathematical explanation of how band diagrams, how band gaps are generated. Just a quick review. We are studying a periodic structure which there is a periodicity in the geometry, and here we want to go to the electromagnetic domain and see how our Helmholtz equation, our Maxwell equations behave in a periodic structure. The whole idea of going to these structures, the whole interesting feature of these equations was this boundary condition that your structure is periodic with a periodicity, let's call it here A, and due to the Fluke theorem we know that the solutions of these structures should also be periodic with the same periodicity as the geometrical periodicity. So this is an important remark in order to keep it in mind. So here, if we combine these 2 equations, we need to, this criteria should be satisfied that e to the minus ik gamma, or here, for example, a, should be 2 pi, because this is going to be equal from this side to the other side if we move by a, and so this will give us that the k should be 2 pi over a. And here I put this equation, this complementary equation here. So whenever I write, for example, kx in my simulations, I mean that, for example, if this is the propagation direction, which is x, there are other directions, I call them transverse, and so this is the normal dispersion equation, that kxx squared plus the transverse squared should be our overall wave vector squared. So when we're sweeping k vector, this means that we're sweeping this parameter, and it means, for example, when it's not equal to k, the rest is going in the transverse mode. Okay, no, this works. Okay, and just a quick review for the physical picture of the band diagram, band gaps. You input the light, and it gets reflected from the surface of your boundary conditions, your periodic bound. So in a range called the frequency of the band gap, the forbidden band gap, there exists no propagation, so your light doesn't propagate there. And one silly question that came to my mind first when I was studying about the band gaps, I said, okay, if we don't have any mode propagating, so what's the deal? Why do we need that? So the need of these structures, for example, in this picture is some sort of a mirror, for example. So you want your light to propagate in a medium, and when it reaches this bunch of structures, this bunch of periodicity, it will just get reflected back because it cannot propagate in this direction. So let's talk quickly, like in about 2 minutes, about what's the origin of the photonic band gaps. Just imagine that you have a medium with a permittivity epsilon 1. So the normal dispersion for this medium would be omega equal k over square root of epsilon. And since my dispersion is even with respect to k, it also be an even function, and it will like be mirrored around with respect to this frequency, to this omega axis. So what happens if I treat my medium as a periodic medium, so if I move by A, it's still epsilon 1, right? So I have originally this dispersion diagram, so I will have to shift it by 2 pi over L. So it gets shifted if I consider this to be my permittivity. So here I will have another curve here or another one curve shifted here. So my structures get sort of folded here. So that's, for example, this is from my initial dispersion diagram. This is from the one that is 2 pi shifted. Here, continue with this one, you find something here, goes on and on, so you get a folded structure going on. And since you know that the electromagnetic modes should be, for 1K should be, if you have several solutions, they should be orthogonal here. For this particular point, I introduced, for example, one cosine and one sine function for these two modes. So let's see what happens. If you do a little bit of math, you find out that due to the variational theorem, that your lowest energy mode should have higher amplitude in the regions that have higher refractive index. So, for example, I call it this cosine mode. And the other one, since it's orthogonal, it should be shifted by pi. So you can see that when it's max, that one is around the minimum. And now let's do a perturbation, for example, and assume that your uniform medium is now reappearing epsilon 1, 2, 1, 2, and by epsilon 2, and epsilon 2 being higher refractive index than epsilon 1. So your fundamental mode or your lowest energy mode is okay. It's having higher amplitude in the epsilon 2 region. The other one is the other way around. And if you look at this graph, it's not making much more sense, because if you remember, when I described the solutions of my wave equation with the boundary conditions that were fluke boundary conditions, the periodicity of my answers should be the same as the periodicity of my geometry, all right? So here, for example, for this particular point that these two dispersion diagrams are coinciding, there's one problem, because these two modes have the same frequency, all right? But this one has higher amplitude in the high refractive index region. So it has effectively a higher refractive index. But for the other one, it's the opposite way. It has lower effective refractive index. So two modes with the same frequency and different n, but here they're having same frequency, so it's not making sense. So everybody is having some problem with this. I want to get a note if everybody has a problem with what I just proposed. If you don't have a problem, let's think about it a bit more. And yeah, we're having a problem with this, and the reason, and how are we going to fix it? So the mode with the higher effective refractive index should have lower frequency, and the other one should have higher frequencies. So this is why your band is sort of opened, and you have a forbidden band gap. So by this simple calculation, I sort of demonstrated for you that for a 1D periodic structure, you should have a band diagram because of this frequency of these points that the dispersion relation is folded, and you have a folded region. So your band should open up, and this is called the forbidden band gap, that you don't have any more propagating. So this is just a little bit of history. One of the first optical band gap cavities by Eli Jablonovich from 1987. So here he put a defect medium in the middle, and then he has some a periodic medium designed here and on this side and that side, and by this he has a defect mode, a mode that can propagate in the middle, but when it wants to propagate in left, towards left and right, it gets total internal reflection to itself and some sort of waves destructive interference here, and so he has he designed one of the first forbidden band gaps for photonic structures. So today what I want to show you is how to simulate and how to study photonic crystal mirror. So something similar like a cut from this design. So you have a waveguide, your light is propagating, and when it hits your periodic structure, which here is a photonic crystal, which is somehow, for example, in case of this being, I don't know, silicon or silicon nitride, you have nitride, you have nothing, you have nitride, you have nothing. So you're modulating the effective refractive index. So once again, light gets into this in this physical picture, which I kind of like, makes me a bit more familiar with this. So this is what we want to make in the end of this session. We want to have this unit cell of photonic crystal, which is here is the cross section, for example, of the waveguide WH. So your waveguide, for example, is like this, and then your light is propagating, and you want to put a mirror in front with the help of a periodic structure, in this case being photonic crystals. Here are the parameters. You might ask why these parameters I just put here. So there is a reason behind each number, except, for example, this one is initially fixed, for example, for my case. The thickness of the film, and the rest you can find it out by simulation. If you want to discuss, we can discuss it afterwards during the breaks. But just for now, we want to simulate the band diagram of a photonic crystal, a 3D one, for these parameters. And in this graph, just a quick remark and recap to what we had yesterday for photonic band gaps, because this line will make, because the origin of light wave and acoustic waves have two different, have one difference, which make the post-processing of your data different from the post-processing of your photonic bandgap with the photonic case. And also when you want to draw your model in COMSOL, because if you remembered yesterday, we just drew our model and started solving. And the reason was we didn't care about the surrounding area. And the reason was, if the surrounding area of your photonic crystal is vacuum, your acoustic waves cannot go there. So thinking optically, it's like a medium with 0 refractive index, all right? So the light cannot be there, or the acoustic waves cannot go there. But here, if you want to simulate this, your light can radiate, or the light propagates in the free space. So you have to modify your model a bit, which I'll describe. And also when you plot your band diagram, you plot your different modes here, you have to consider that in this dashed black line is called the light line, or if you want to imagine a 3D, it's called the light cone. And this will divide your omega versus k platform into two regions. The region above the light line, which is here, and the region below the light line, which is here. And this light line is just the normal dispersion of the free space. It's omega equal the speed of light times your k vector. So if any mode sits at the top of on top of this line here in this region, it means that the effective refractive index is smaller than 1, and that mode is not propagating. Okay? So here we don't, whatever band diagram we get here, we don't care about, because those are not the propagating modes. So we just care about the area underneath this light line, which, for example, is here. And here I'm presenting you a band gap which is not a full band gap. It's called incomplete band gap, because this purple mode, okay, I don't have the legend. This purple mode is a TM mode, a TE mode, this blue one is a TM mode, and the mode that is appearing again here, it's again a TE mode. So you have one TE mode here and one TE mode there, so you sort of have a incomplete band gap just for TE mode. So if you're just inputting TE mode to your structure, this is a band gap for your mode and gets reflected. So let's start the design and start to simulate this. This is the modification that I want you to always think about when you are simulating an optical waveguide or an optical, for example, structure, is that, for example, here you see this is my photonic crystal, and here I put a big box around it. And this box, I call it the air box, for example, and I put the perfect electric conductor boundary condition on the edges, on the surfaces of this air box. And it's significantly, I assume it to be larger than my structure because I don't want to simulate the whole volume for COMSOL. I want it to stop at some point with the PEC boundary condition. So two modifications with respect to phononic crystals. One of them is having the air box around it and putting the PEC boundary conditions on the edges. So if you can download everybody has the model, let's start to check what we can do. Yep.
Cannot download actually I cannot, there is nothing in the folder, at least for my computer.
You cannot access the folder?
I can access the folder, but there is no model inside. Yeah.
Ah, okay. That's weird.
Just put it not into the slides folder, but in the software COMSOL folder.
Yeah, but it's also... are you sure nobody deleted it? Because I downloaded from that, but I'll upload it right now. Again.
Maybe just refresh.
I tried, I guess, refreshing.
I see it there. I don't know what.
Oh, okay. Somebody's messing with me a bit. Okay, that's fine. All right, let's do it again. I think I can upload the downloaded version, which is deleted somehow. Okay. So till it's uploading, I do the same thing like yesterday. Come here, make a folder for myself. Turn 1D. Okay. Okay. Can you refresh it, everyone? See if it's still there. Okay. Okay. So while you all are downloading the file, I'm just going to actually, I was planning to have an exercise and trying to draw the model, but I thought that it might be more useful to talk about the origin of the band gap. I hope we're on the same page on this. And if I will go through the designs, it's super simple, just all the steps one at a time, and I will show you. Okay, tell me. The PEC boundaries, okay, we'll discuss it in the model because when we have our optical structure, the COMSOL will solve it, whatever it can propagate in. It's air around it and will solve it in a huge space. But we all know that the light cannot go far enough. Yeah, it does, but there is a transverse function for the free space, so it cannot go, for example, when it comes out of your structure, it somehow damps after a while.
Ah, okay, so
yeah, I don't want to simulate the whole region, the whole area possible.
you're low for losses.
Yeah, if you do that, you will get the result. But I just want to make my model a bit smaller. So I just, for example, extend the dimension of this air box like 5 times, 10 times larger than my active structure, and then I will say, okay, this is PEC, so this is when your field is 0. I don't want to go further than that.
Why not PML or scattering boundary condition?
It doesn't work with the Duplicate condition. It doesn't exist. It's Duplicate condition.
So the perfect electric conductor boundary condition is now where we put the periodic boundary condition?
No, it's different. We just put PEC like in Z direction around it, not at the faces that are fluke. Yeah, we'll get to that. Sure.
So is this PEC also impedance match?
What do you mean?
Like with the PML to ensure there's no back reflection.
You can also put like PML around to make sure there's no back reflection. It doesn't make any difference. Yeah. You should get the same result, as long as it's far enough. All right, so with the definition of the parameters, I also put the parameter text file for you. So if you want to draw it once yourself, this is the parameter. These are the parameters. My material here is silicon nitride and vacuum. And into the definition, into the geometry, I again have a work plane, and I first draw my photonic crystal work plane, just a 2D. Like this, something like this, and then I extrude it here with this option. I extrude it with the thickness of my nitride here, and you can see it's extruded here, and then I draw a box around it, which I usually call it air box, but or maybe in this model not. You see it's around your structure. So Simon, coming back to your question, for example, for this surface, this one around your structure that the light can go on and on, we just put PEC to stop the simulations at this point. But for these faces, we will put fluke boundary conditions. All right? So, and then form a union, so I build all of my geometry. Everybody has access to the model and is following me? All right? So materials for silicon nitride is my photonic crystal, and the rest is vacuum. And here, coming to the boundary conditions, I put PEC boundary conditions for these surfaces. You see, the surfaces in the Z direction, and these two that I'm not really interested in. But for the faces that are periodic, even for the airbox, I will put periodic boundary conditions, for example, for the recurring faces of the airbox. If you see here, for example, and here I add a periodic condition, a fluke condition, and I just want to study in the X direction, just a 1D. I have 1D photonic crystal, and as usual, as like yesterday, this is the Kx, which is the K normalized time, pi over A, which we already derived in the beginning presentation. So for example, here you see that this airbox, this face of the airbox, and also this face of my photonic crystal has fluke boundary condition, as well as the other side. Okay. And for the meshing, we do exactly the same thing. Like yesterday, here I named the meshing propagating walls, and this is the copy, which we remember from yesterday that we copied exactly the faces that are fluke condition, and they should be periodic and they should be the same. So here I have copied, for example, maybe the airbox and the photonic crystal face of one side, and copied the mesh over to the other one, and one mesh for the remaining part of my structure that will cover the rest. And for study, we want to study the band gap, so we put a parametric sweep on the normalized K vector, and then we sweep it from 0 to 1, and solve for the eigenfrequencies. So eigenfrequencies, because this is a terahertz, something that the band gap should be around 770 nanometer, which is around 300, 400 terahertz. There is no reason to start your study from 0, so I start from 200 terahertz and searching for 30 modes manually. Okay, let's get back to this view, and you can press study. It takes a couple of minutes, maybe 2, 3. And meanwhile, I just want to show everybody is running, and if somebody has a question while it's running, we can get back to it. So coming back to this picture, I want to recall once that when we want to make an optical simulation for periodic structures, we have to take care of the post-processing of our data. So here doesn't mean that the light is propagating because of this light cone that is the dispersion of the light in the free space. So whatever is here has the n effective smaller than 1, less than 1, so it cannot propagate. And just think about what we did for the phononic bandgap. We didn't put this line. And if we were about to put this line, just a simple analogy would be the acoustic waves. Your acoustic waves cannot propagate in vacuum. So their sort of refractive index should be 0. And this line, the slope of this line is c. And that case would be c over 0, which will make it steeper and steeper, and it just sits on this axis. So whatever is here for a phononic structure is propagating. So that's the difference for post-processing. And for your model, remember that you should always consider the surrounding area because the light can propagate in the free space. So and it's always good to have some to limit your structure in a way that it matters. For example, I don't want to put these PECs very close to the structure because they would disturb the field. So I want to put them as far field as I could.
This question was already asked, but could you say once more what happens if you use not conductive boundaries in the
like PML?
But say PML
A perfect match? I don't think might be an issue.
No, but will it change the result that you are getting?
It shouldn't.
But still you have this region where the effective propagation index is inside the light cone.
Sorry?
Because it's not physical if the mold is propagating inside the light cone.
Yes.
So will this outcome change if you use some other boundary conditions?
I don't think so. It should be the same. Because I just put this to limit my model and put some boundaries around it. So I don't think if we make around surrounding like PML, we just assume there is no reflection, might be a difference. But we can try, of course. So let's see. Okay, mine is finished. You can see different modes. Here I added a 1D plot. Here, since the spacing of the modes are a bit better than the phononic case, you can somehow see the bandgap here. But I would like to come back to my favorite MATLAB code and see what happens. That was it, right? Yes. If we save it. Okay. So run it, for example, here I put the number of modes that I solved, I put it to 10, so these are these lines don't look as nice as what I put for the presentation. There were about 100 points, so but this is, you see, this is a light cone, and here the light, you're inside a light cone, so your refractive index effective is smaller than 1, and we care about this region. And here, for example, you see an incomplete bandgap for your TE modes, because this one is TE and also this one. So if you control the input light, yes?
I don't understand what the incomplete bandgap is.
Well, this one, because the number of modes I put, the number of K sweeps I put 10, it's not really correct, and maybe this point should be connected to this one. It's a problem with the, if I increase the resolution, the result would be better.
Very basically, what is an incomplete?
What is the incomplete bandgap? So for a case of complete bandgap, you have something like this, that there is actually no mode propagating. All right, so you have no mode from not from TE, TM, no mode family can propagate here. But in this case, if you look here, you have one mode propagating here, the other one propagating here, and a bunch of modes propagating here, all right, in this frequency region. But this mode is from a different mode family than this one. So if your input light is polarized, and it's just, for example, TE mode, this mode doesn't exist. This one does not exist in your dispersion. So you only have this one, this purple one, and for example this orange one. So here you will have a band gap for it. This is what it's called an incomplete band gap.
Absolutely important. Can you go to the magnifier?
Yeah.
So this is sort of called quasi band gaps, basically gray area, and it's very important because to create a band gap, you normally need the effective index contrast. The larger the contrast is, the bigger the band gap is. The problem with photonic crystal is that the photonic contrast is between vacuum, which is the whole, a little bit of vacuum, and a little bit of silicon around it. So it may be a factor of basically 2 to 3 difference. So this is not so big of a difference to create a huge band. As you can see, the complete band gap area, which is at the top of that gray area, is very small.
Mm-hmm.
But fortunately, you can have quasi band gap. By that I mean we can have band gaps, for example, for only TE modes. The blue line is a different polarization, and by definition they should be orthogonal. So if you have a TE polarization, you shouldn't couple. But there is a risk here. Like if you have any imperfection in your system, like asymmetry or something, you might actually couple
Due to scattering.
The idea is like, for example, photonic crystal or photonic crystal cavities confine the light, and we use this quasi band gap to confine a certain polarization, let's say TE. And if by any imperfection or anything, like this TE couples to TM or scattering or whatever, that TM mode is free to propagate. So that would be ultimate, basically, loss, or let's say ultimate limit of Q in this photonic crystal cavity. Okay.
Right, so just coming back to what Amir just explained to you guys, for example, if my waveguide here is a perfect rectangle, so my TM mode, for example, would be like here, the other one would be like here, so they're orthogonal, so they cannot couple, but if you have some imperfection somewhere and there's a scattering, they can couple to each other and you lose your ideality, let's say. So with that, I think I'm finished, and if there is any questions, I'm happy to answer.
I have a question on your meshing of the photonic crystal.
Yeah.
Errors mostly.
Yes?
So, do you have to consider discretizing the mesh with a smaller or higher resolution than your waveguide that you're solving for?
Why should I do that?
Because in principle, if you discretize the mesh with a higher or with a coarser resolution, then your mesh can't really see your wavelength, right?
Yeah. All right. Okay.
So does that make a difference in your simulation?
It is already the case, right? The mesh is
Yeah, the mesh. Yeah, it's already the case. It's.
in the size,
Yeah.
of the size of the unit cell.
But don't you have to discretize like a wave with at least 6 points to get it approximate?
It is probably that.
Mhm.
I mean, you can always mesh it better, and then the general rule of meshing is like there is no good answer to how good mesh is. Just need to mesh it finer and see if the result actually depends on the meshing. If it depends, the meshing will answer.
Yeah.
Yeah, so this is a general question for any simulation, right? It's not just for this. I mean, like how fine the mesh is a good mesh. So this is one of the tasks that a simulator needs to check. We don't have time to go through this, but for any simulation, you need to increase the mesh, see if your result depends on how fine the mesh is.
There was something over there.
Yeah, I was wondering why the solver finds these for fitness.
Because it does not care about our light cone, it just fixes K and solves.
Physics, because we are just plugging the physics equations into the solver, right?
Yes.
Where is in our physics the light cone?
Well, it's in the first equation that I showed you. It's kx squared plus your k transverse x squared equals k squared. So in that case, the other one would be imaginary, right? Because it will be more than your k, and so it's like the square is minus. So it doesn't care about the transverse, just solvings in the x. right? Yeah, they just decay super fast. Yeah. Yeah, yeah. Decays in the transverse direction very fast.
It's only physical density as long as K transfer squared plus K propagation squared is equal to omega 2 divided by CG. That's if, as long as you have that condition.
So it is physical, but actually going.
Yeah, it's not just below this line, above this line point, the modes are not confined. That's what we want to do.
Okay. Everybody has a band gap? And if you had any questions about these numbers that I raised the question, why we use, for example, 500 for the width and our small and the large diameter and small diameter to be these numbers, we can discuss it afterwards. Because you have to take different simple analytic calculations and some simulation sweeps to get these numbers. Okay. So thanks for your attention.